Look closely at the natural world, and you'll find that purity is an illusion. From the air we breathe to the water in our rivers, everything is a vibrating molecular mess of different substances clashing together. We call these heterogeneous mixtures. Their components are unevenly distributed, clumping together in a physical tangle. Solutions and alloys represent the opposite extreme. These are homogeneous mixtures, a uniform blend at the molecular level, where chaos is organized into a mathematically even grid. To use these mixtures, we must calculate their concentration. In fields like medicine or agriculture, knowing the exact ratio of a dissolved substance determines if a solution is effective or potentially harmful. Dr. Dilip Mahalanobis proved this utility with his work on oral rehydration solution. He used a precisely calibrated concentration of salt and sugar, creating a mixture that has saved millions of people from the effects of deadly dehydration. Controlling these ratios allows us to take raw, unpredictable matter and turn it into a reliable resource for our health and safety. Once we understand a mixture, the next challenge is ripping it apart. We start by tackling macroscopic suspensions, like human blood. The paperfuge achieves this by exploiting density. By spinning a sample at high speeds, the heavier red blood cells are physically forced to separate from the lighter plasma, pulling order out of a biological soup. We can do the same for muddy water. By adding a single alum crystal, or fitkari, we force the scattered, chaotic dirt particles to clump together. These newly formed clumps become heavy and can no longer remain suspended. They succumb to gravity and sink to the bottom, leaving clear water behind. By manipulating density, we use the planet's own gravity to strip away the visible mess from our most vital liquids. But as we scale down to perfectly blended liquids, density manipulation fails. To separate molecules that have seamlessly merged, we have to look for their thermal breaking points. Sublimation is one such thermal bypass. A solid like camphor can be heated until it skips the liquid phase entirely, turning into a pure gas that we can isolate. Distillation takes this further. In a mixture of acetone and water, each liquid reaches its specific boiling point at a different time. By holding the temperature at exactly 56 degrees Celsius, the acetone vaporizes and leaves the water behind. This science is the heart of the Deg-Bhapka method in Kannauj. Indian artisans have used these thermal limits for generations, capturing pure perfumes from flowers and earth by boiling and condensing their most volatile molecules. Identifying these invisible thermal boundaries allows us to extract delicate fragrances and industrial chemicals from what once seemed like a single, unbreakable liquid. At the most microscopic level, separation requires us to test how well a substance dissolves, its solubility. In chromatography, we use this to race molecules against each other. As pigments travel up a fiber, they separate into distinct bands based on their individual speed and solubility. But the ultimate way to achieve purity is through crystallization. When a hot, saturated solution of copper sulfate begins to cool, the molecules are forced to make a choice. As the liquid cools, it can no longer hold the solute. The copper sulfate molecules expel impurities, binding together into precise geometric structures. It is a moment where the randomness of a solution is traded for the rigid mathematical perfection of a crystal. Sometimes, however, nature hides its mixtures in plain sight. A colloid, like milk, looks like a pure, uniform solution to the naked eye. We can expose this using the Tyndall effect. When a beam of light passes through a true solution, it remains invisible. But in a colloid, the light hits hidden, suspended particles and scatters, which illuminates the particles and reveals the mixture for what it really is. By identifying these hidden properties, we gain the ability to untangle the substances around us, allowing us to isolate the specific molecules we need to cure disease, produce energy, and build more predictable materials.